All right, so starting off with, say, a number bonds to 10 book, how do we teach number bonds to 10? And really the first thing to say is that you do it using fingers. Occasionally you'll hear people say that children shouldn't count using their fingers, which to me is crazy. I once had a student whose grandfather was Chinese, and I think there's a school of thought in Chinese teaching that the children shouldn't use their fingers. And she told me that he used to stand by her with a ruler, and if she showed her fingers, he'd hit her hands with a ruler. So unsurprisingly, she was quite traumatized and needed help from me, you know, to try and fix that. But she was very scared around numbers, as you can imagine. So obviously, don't do that. I mean, it may seem obvious how you count with fingers. You go 1, 2, 3, 4, 5, like this, 7, 8, 9. You can, of course, take fingers away if you're trying to make someone understand that, you know, if you have 10 fingers, you take 2 away, then you've got 8 fingers. And if you're doing your sort of finger drill warm-up, you might say, all right, I've got 4 fingers. I'm showing 4. How many more to get to 10? And then you can go 5, 6, 7, 8, 9, 10, like this. You can count knuckles as well. That works. The other thing you can do is, if you're counting on, you can say that you've taken the number. So you can say, right, I've got 3, and I'm going to hold that in my hand, and then I'm going to go 4, 5, 6, 7. So therefore 3 plus 1, 2, 3, 4 is 7. Okay, so those are 2 ways that I use to teach with fingers. And yeah, you know, if someone's fingers are a little bit like stabilizers on a bicycle. Can both of you ride bicycles? Yeah, no?
I can't. I mean, I tried learning, but I just kept falling.
Right, got you. Okay. In which case you probably would have, you know what I mean by stabilizers then, because you would have had those at some point. Yeah, so fingers are a bit like stabilizers. They sort of, or another way of thinking about it is they're like, I don't know if you ever sort of look in a pond and you see tadpoles and they've got the tail and then those little legs developing, and then at a certain point the tail drops off and they can jump with their legs. So finger counting is a little bit like the tail. You know, at some point it drops off and they can spring off with their legs, but you know, it's a natural process. And what happens as someone starts getting faster and more confident is that they'll just use their fingers less, and then at a certain point they start being memory based. Actually, that's an important thing to talk about, is that interface between method and memory. Method is really a fundamental for building confidence. Okay, it's the safety net. So, you know, if I'm saying, all right, 6 plus 1 is 10, and I go, okay, 6, 7, 8, 9, 10, there's 4 more there. If my memory is failing, then this is my method. Okay, and it's absolutely fundamental to give a child a method. You might sometimes encounter, and I've got a student like this at the moment, they have a real problem because they've been on times tables rock stars, and they don't have an adequate strategy for working out multiplications. And so timetable rock stars for them is an issue because they can remember most of them, but some of them they can't, and then they don't really have anywhere to go. So there is, speed for speed's sake is not a good thing, right? We have to be, we're looking to build speed and automation, but we have to base it on method. And I suppose I can just show you this. This is a diagram I use to explain this to people, to students, really. So up at the top here, we have what I call hyperflow. Speech is hyperflow. I said this, I think, in the first webinar. It's where your brain is not really conscious of formulating things. It's just an automatic process. Hyperflow can happen in numbers as well. It's when you start doing about one question per second. So if you're doing 20 questions in 20 seconds, you're pretty much getting to hyperflow. And then below that, you have flow. All right. Flow is where the answers are flowing out, but you're still not going crazy fast. Right? In hyperflow, you're looking one question ahead and your hand is writing the answers sort of after your thought process. Flow is where you're just kind of, maybe you're doing 20 questions in 30 seconds or a little bit faster, something like that. And then underneath that, you've got method. And method's where it's like, okay, what's 9 times 6? You see the question, you can't remember the answer. So then you're going to go to your method. Okay, well, 10 times 6 is 60. And what's 6 less than 60? 59, 58, 57, 56, 55, 54. Yeah, you might even use those fingers to count that, because when you're under pressure, sometimes you need something, you know, as reassuring as a finger count, and that's absolutely fine. And we've got to make sure that there is a connection between these 3 states. Yeah, that's what's really important. So a student knows that if they're in a flow and then their memory fails them, they can pop down here into method, and they've got a way of working it out. And this is really this is like the essence of what I've been talking about these past few webinars, because we're not trying to create flow for sort of hyperflow for hyperflow's sake. We're trying to build a system which allows a student to accelerate up to hyperflow, but they can always come back down again if necessary. Okay, so there's your method. And then underneath method, you have what we can call a sort of, one of my students used to call it the paella panda zone. Which is basically where you sort of fall into a funk and can't really work anything out. Okay, and that's what happens if you don't have a method to go to. It's the point of sort of confusion, maybe panic, and you can't really get anything done anymore. And maths is uniquely good at opening the gateway to this place, right? Anybody, myself included, and I've been to paella panda zone, you know, if you put the spotlight on someone and give them something they can't do, the brain kind of locks up and you're like, I can't do it. All right. And then if you go there, if you hit that, then you have the wall of death. And that's what you hit if you don't have a way to get back into method. Okay. If you're in hyperflow and it all breaks down and you pop out of here, you got nowhere to go, then it's a tumble down and you end up somewhere back in here. All right. So that's a slightly impromptu explanation of how this is meant to work, but a useful thing to bear in mind. Okay, so finger counting gets us to 10, right? What do we do about this 10 threshold? Thresholds are really important. Students tend to have their first issues when they get to the 10 threshold. A lot of students I've encountered will have problem with something like, I don't know, 8 plus 7 or 9 plus 6, something like that. They don't quite understand what happens when they go through that barrier. And so how do we help them through that? So the answer is we use a number line, which I call a perspective line. I call it a perspective line because it's designed to go towards a vanishing point. And the concept here is what I call spatial maths. It's starting to understand numbers in terms of space, in terms of quantity, instead of in terms of quantity. Clearly, numbers can be about quantity as well as space, right? Fingers, that's a quantitative way of understanding numbers. But what happens if you have too many dots or too many sticks or too many of anything? It starts to become quite hard to contemplate. It becomes less intuitive. You start guessing. You know, you can't count 100 things very quickly. Whereas if we think in terms of space and distance, I think it's easier to understand. So that's what this is. It's called perspective line. And if we took a sum like, let's say 6 plus 8, then we'd be using number bonds to 10 principle, and we'd be saying, all right, I'm starting here at 6. Here's the 10. Yeah, I'm going to go 7, 8, 9 to 10. And then we're going to say, and how many have I gone? How many is it from 6 to 10? How many spaces? How many stops? I quite like just drawing circles in the gaps because you can't really go wrong. Sometimes people can get confused about, do I count 6 when I'm moving forward? Is it 6, 7, 8, 9, 10? And you're like, well, no, because that would be 5. But nevertheless, it's one of those little points of confusion. If you draw the little circles on the spaces, you can't go wrong, right? It's 4. There's 4 spaces there. So we know that we're counting 8. We've used 4 of them, 1, 2, 3, 4, and we know that there's going to be another 4 left, 11, 12. Okay, and we can draw those on there. So it's about saying to the student, okay, how many to get to 10? You know, if they've been working in their number bonds to 10 book, they'll know the answer most likely. And if they don't remember it, then they can work it out using their fingers. And then how many are there beyond 10? You can always render 8 as a tally if you want to as well. You know, 1, 2, 3, 4, 5, 6, 7, 8. And you can say, all right, how many have I used from 6? I've used 1, 2, 3, 4. How many are left? 1, 2, 3, 4. And then you can draw these in as we go up. I've missed one, haven't I? 6, 7, 8, 9, 10. Yep, there we go. That's the final one up there. Okay, so that's how to start.
You were right the first time.
Oh, was I right the first time?
Yeah, you were right the first time. There's 8 on there.
Yeah. I just meant in terms of getting up to the final answer. You're right. I had 4 tallies, but I hadn't got up to the 14. I left off the 14. But thank you for checking. Yeah. So that's how to deal with the 10 threshold, and just encourage those processes. So how many to get to 10? And when we say how many, what we really mean is how many ones to get to 10. You can also say gaps, stops. I sometimes describe this as being like a tube line. And if when we start talking about multiples, you know, you can say, well, I'm stopping. We're doing multiples of 3. I'm stopping every third stop on the 3 stops. Yeah. And actually, this is pretty central to the whole way that I teach maths these days, is using this perspective line. And you can actually use it for a lot of different things. You can use it for multiplication, you can use it for division, and subtraction is very useful for it as well. But anyway, that's getting through and above the 10 threshold. And this is what you would use to transition from number bonds to 10 to number bonds to 20. Okay, once we get to number bonds to 20, you know, if we have something like 8 plus what equals 20, then, oops, I only discovered how to draw the straight line about 2 months ago. I've taught literally thousands of hours on this program, and I never knew that you could press one button and draw straight lines. So I had to sort of perfect my ability to draw straight lines freehand. Didn't quite get there, but you can imagine just discovering one little button and then, yeah. So 8 to 10. We're questioning how many to get to 10. Answer 2, obviously. And then at some point, the kids will start realizing that it's always 10 to get from one round number to another round number, assuming they're 2 digits. Okay, so they might start putting together that it's 2 plus 10. But equally, for a while, they might need to be going 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Yeah, they may still need to see those ones. But you're looking for the point where they're going to go, okay, 8 to 10 is 2, 10 to 20 is 10, and therefore the answer is 12. Okay, And, you know, once they're starting to do that nicely, you're going to push that envelope a little bit so that we're going to go, what 7 plus what equals 22? And we're going to start going, all right, that's to 10, that's to 20, there's 22. So it's, you know, 3 here, 10 here, 2 here. And then you're asking them to add the numbers up using the biggest number first. The analogy is if you were building a pyramid, you know, you wouldn't build it using the smallest number first, right? So it's sort of a logical process of stacking those numbers up, 10, 3, and 1. And it's a useful habit to get into. One of the things that we try and encourage students is to use one method as often as possible for all questions, right? If you have one method that you're extremely good at, then you don't have to think about methods. You can just crunch the numbers and get to the reasoning part of the question if, you know, if that's what the question is requiring. And as you'll see, we can use perspective line for lots of different questions. Okay, so there you go, that's up to 22. Now, as you can probably imagine, we can use this for pretty much anything. If I'm going 35 plus something equals 54, then we can start to do this here. All right, and each time we're just going, all right, it's 5, it's 10, and it's 4. Build them up, 10 plus 5, 15, add 4 is 19. Okay, so we're trying to navigate this number space using this method, always using the round numbers and the gaps to the round number. We'll go through 2 digits, we'll get up to 3 digits. So this is a classic point of confusion. You know, if I'm doing 73 plus something equals 105, again, 73 to 80 to 100 to 105. And we're starting to get across that 100 threshold in a logical fashion. And that's the 100 threshold is all you need at the sort of for the first, you know, for like key stage 1, I suppose. You might start getting into bigger 3-digit numbers, but in terms of demonstrating this method, is that clear? Sort of making sense? Yeah. All right, lovely. Now, we may also get something like 54 plus 28. Okay, so this isn't the gap question anymore. It's not saying if we start at 54 and we're going somewhere, how far are we traveling? This is saying we've got 2 quantities. Now, you can do perspective line on this, but it's definitely less intuitive. And I came to the conclusion that for a question like this, I'd probably prefer just to do number splitting. By which I mean we're going to split this 54 into 50 and 4 and 20 and 8. All right. And then we're going to add, again, bigger numbers first. We're going to go 50, add 40, 70, and 4 add 8 is 12. Or we can just go 70 plus 8 plus 4. And eventually we end up at, you know, 78. Now, here you could see, well, we've got 78 to 90 is 2, and then there's 2 after it. So if we want to use the perspective line to get across that threshold, we can. But generally, if we're dealing with, you know, round numbers that are easy to add, I find this a faster and more intuitive way of adding this kind of question. There's no harm in sort of looking at different ways. Sometimes students will have a preference for one style or another. And it's trying to find the optimum way to do, you know, all different types of questions. So there we go. There's number splitting. If I was doing a 3-digit, you know, you might have 325 add 234. Then I'd probably want to go 320 and 5, 230 and 4, and I'd be saying 559. Okay. Now you'll notice that what I'm not doing is doing traditional sort of long addition, which is, 354, what was it? 325 and 234. I'm going to change it up a little bit. So I'm going to go 4, 6, 7. Now, this is what everyone gets taught, myself included, at school. And obviously, we're going to go 4 plus 7 is 11. 5 plus 6 is 11, add 1 is 12. And 3 plus 4 is 7, add 1 is 8. What do you think the problem is with that method? Any ideas?
Kids usually mess up carrying forward.
Carrying forward, yeah. You can put them at the top or the bottom. The problem is that it gives no real sense of number, right? You're adding two numbers that are in the hundreds, and yet the calculations you're doing are in the units and tens, really. 7 add 4 is 11, 5 add 6 is 11, add 1 is 12, 3 add 4 is 7, add 1 is 8. The biggest number we've talked about is 12, right? Yet the answer is 821. And there's no real sense of our journey to 821, right? I call this sort of blindfold maths or eyes shut maths, because we're trusting a process to arrive at an answer, but we have no real idea of the journey. It's like, taking the tunnel through the mountain instead of walking over the mountain, although there's a problem with that because, of course, it's quicker and easier to take the tunnel. But it's just this. It's one of the major problems with maths is that we come up with a set of rules, we give them to kids, we expect them to follow them, and yet they don't get it. They don't understand why the answer is the answer. So this is why if we split this number up and we go 350 and 4 and 460 and 7, we're immediately starting to see the numbers that are involved, and we get a sense of size. Like 300 is a big number, 400 is a big number. Yeah. The adding of them is pretty easy, because as long as we know what 4 plus 3 is, it's pretty logical that you just add the word 100 after it, right? And we sort of, the addition is fairly easy. So we're 760. Now 760 add 50. Well, we could use a little perspective line picture here to get us over that. 760 up to 800. Well, we know that it's 40 to get to 800. It's 10 afterwards, so we're on 810. Yeah. And then we've just got the 4 and the 7. Do the 7 first at 817, and then the 4 finally to 821. So, yeah, that's why I don't really like old school column addition. Now, kids are still being taught old school column addition, and we're not telling them to sort of throw it out the window and never use it. What we're trying to do really is give them a better way of doing mental arithmetic, but we can always use this to check an answer. All right, so I generally advise that the old school techniques, we're not trying to unteach them. They work, they get us to the right answer. We're trying to develop a strategy which is superior for mental arithmetic, and we can use this, if we want to, as a sort of end of exam simple check on our answer. Was our answer correct, yes or no? Okay, so that's the order in which I'm trying to get students to work. Firstly, you use your fast mental strategy, and then you can check it with the old written strategy if you want to. Okay. Now, subtraction. Subtraction is one of the hardest things to explain. Yeah. If you go through old school, I don't know, like 2, 3, 4, take away 1, 7, 9. You've got to explain to someone why you're going to borrow 1 from the 3, right? And give it to the 14. So to give it to the 4 to make it 14, and knock that one down to a 2, and then subtract the 9 from the 14. it immediately gets very difficult to explain adequately. And, you know, a lot of ink has been spilt on how to do this properly. Okay. Again, they're going to learn it at school as a method. They may or may not be getting that method right. They almost certainly will not understand what's actually happening number-wise. However, if we do a perspective line and we go 179 and 234, and then we go 180 and 230, and then in the middle we write 200, depending on the student, they may need you to put the tens in, but we're going 1, 20, 30, and 4, and we're pretty quickly seeing 55. Okay, it's way easier to explain. It's completely intuitive, and it's very easy to do mentally, right? I'm writing this stuff out, but at a certain point, when you've imagined this perspective line enough times and you just get in the habit of seeing those zeros, you know, this stuff becomes a very fast mental strategy. And I, having never been taught this and, you know, sort of teaching maths and explaining maths to kids, basically ended up concluding that this was the thing that they understood most readily, and certainly for me, the thing that I find the easiest. You know, now this is just the way it sorts itself in my head, and that's how we, you know, the direction we're trying to steer the students. Okay. So yeah, there you go. There's perspective line, and again, if necessary, you can use the old method to confirm your answer. All right. Any questions so far? No? Okay. All right, so multiplication. Oops. Now, multiplication, we have one fundamental problem, which is that this symbol is generally called times. Okay. But what does times mean? Right? 2 times 6, you're probably both going, it's 12. And you know, that's because you probably learned your times tables. But times doesn't mean anything in modern English. When the vocabulary of maths teaching was first invented, I don't really know when it was, but let's just say that it was quite a long time ago. Times, I think, meant something different to what it means now. And what really times means is lots of. Yeah. So 2 times 6 really means 2 lots of 6. And if we were going to draw that visually, we would say, you know, we can do it as dots. Yeah. 2 lots of 6. Maybe we can do a bag around them or something. I quite like to talk of them in terms of gold coins, because kids like to think about gold and treasure. You know, it sort of makes it a bit more relatable. If you've got some dice, you know, you can throw those dice out and arrange them to show this. We can also, of course, think of it like this. If I start at 0 and travel 6, I get to 6. And then if I travel another 6, I get to 12. Okay, so 2 lots of 6, 2 6 gaps. And this, of course, plays into how we perceive a times table, right? Are we going to try and imagine 12 bags with 6 coins each? Or are we going to try and imagine traveling up, you know, some kind of line? My line is not long enough. It's one of those weird skills that you develop, is working out how to space. Like if you know you've written a line, you've got to cut it into 12 pieces, like a classic fraction thing. Learning how far apart to do the lines, clearly I still haven't mastered it. 6, 12, 18, 24, 30, 36, 42, 48, 54, and then 60, 60, oops, 66 and 72. Yeah, how do we conceive that? Is it easier to imagine traveling up that line, stopping every sixth stop, or is it easier to imagine 72 gold coins and 6 in each bag? I don't know, what do you guys think?
I think like traveling up would be easier.
What do you think, Moggies?
I guess the progression makes more sense.
It's, to me, it seems easier. You know, I'm aware that people can see things in different ways, but it's like I said at the beginning, it's pretty easy to do, you know, numbers 1 to 10 because you've got your fingers there, and it's just like 10 things to imagine. But imagining 72 things is quite difficult, right? It's that point at which you start to glaze over mentally. You're just like, no. and it's that point in when a kid does that, that's when they start getting switched off, right? We all do it. You know, if someone sat me down, I mean, someone sat me down and started explaining about like pottery shards and their importance in or rather the sort of chemical formulation of pottery shards. I'm drawing on my sort of worst academic experience, which was a year doing archaeology, a term doing archaeology, which I have to say I didn't enjoy particularly because it was, you know, was quite it's quite dull. But anyway, I think the space makes more sense, and when we come to multiplication, it's very important to do multiple streams. Okay, it's one of the first things I do with a new student. I'm just like, okay, well, let's count in twos. Can we do 2s to 24? And they're going to go 2, 4, 6, 8, 10, 12. 9 out of 10 will stop at 12, and then they'll go 14, 16. Some of them might just get stuck there, right? Because they're kind of parroting it like a poem, and they haven't really built the ability to flow up and down that line. Important word, down that line, right? Everyone can count up. I've never met one student who can count down as quickly as they can count up. Why not? I mean, it matters just as much to come down as it does to go up, right? Otherwise, you know, the top of the shard would be overflowing, wouldn't it? People would be you get the idea. So yeah, the fluency along a multiple stream is really, really important. And you know, we want to ultimately build it so that there's the understanding that underneath those 6 gaps there are 1s, right? Crossing thresholds is always an issue, and let's just say we're coming down from, you know, we're doing 54 to 48, right? That may not be obvious to somebody that 54 take away 6 is 48. So we're going to go, how many to get to 50? And then how many are there still to go, right? So we know that it's 4 to 50. How many are left of that 6? There's 2 left, 50, 49, 48, right? It's a very logical process. And if you break it down to 1s, I don't think I've ever met a student who isn't able to do it, all right? So we're just constantly referring to that easier level, you know, going back down to the 1s if we need to, just to allow people to comfortably get through these thresholds, which otherwise might be causing them consternation, causing them confusion. So there you go. That's multiplication. Now, what about division? Well, division is, you know, there's a lot of problems with the word division as well, right? We saw that, you know, times doesn't really mean anything. Well, division sort of still means something. You know, we can understand that division means the dividing of something. You know, a better word for it is splitting. And there's 2 areas for this. One of them is division is the inverse of multiplication, and the other one is the splitting of 1 into fractions. So if we take, let's say, 45 divided by 5, well, one trick that I like is, to say, well, if we reverse this, we flip the sign. So the opposite of divide is times, and the equal sign goes over here. Then we just end up with a multiplication. Something times 5 is 45. How many lots of 5 make 45? We can, of course, see it on a line. If we're going to divide this space into 5 pieces, what does that start to look like? And you can encourage students to try a number, right? What seems logical? Okay, so what seems roughly about the right amount? What if we try 6s? Then you get to go 6, 12, and so on. And you'll realize that the 6 isn't going to land on the number. So you can do a bit of exploration like that. What if we go to a fraction? What if we go to, let's say, 1/7? And we want to know what that is as a decimal. What would be your go-to method here?
I divide like 7 divided by 1 and then find the decimal places.
Yeah, so you do a bus stop. Like this. Yeah. Yeah, and that is it's an old school method. It's still useful. Certainly wouldn't throw bus stop out of the window. What's quite fun though is to try using a perspective line on it. And the question always is, this is really one of the key topics, certainly up to 11 plus, and it fits into the fraction, decimal, and percentage triangle. All right. So these are basically the same thing expressed in slightly different ways. And the way that I like to do fractions to decimals is this. We remember that it's really an equivalent fraction if we're going to a percentage, right? 1/7 as a percentage, we have to convert it to a fraction out of 100. Okay, so, and once we've got our percentage, we've also got our decimal, because the percentage is the decimal multiplied by 100. Okay, so the question is, 7 times what equals 100? Okay, now what we're going to use is we're going to use a little bit of speculative maths, right? So we're going to say, okay, so I know that getting from 0 to 70 is in sevens is going to be a times 10, right? 10 lots of 7 gets me to 70. Now, we may be good enough at sevens to know that 4 lots of 7s is 28. And you start to see the importance of that multiple stream. If you know your multiples of 7 really well, then you can see that 70 plus 28 is going to get you to 98, and that is a 4 multiple. All right, so by now we've seen that we've used 10 lots of 7 to get to 70. Again, this stop analogy, we've used 10 lots. Is that going to be right? 7, 14, 21, 28, 35, 42, 49. No, got that wrong. Anyway, you get the idea. So we've used 14 to get to 98. So at the moment, we've got 7 times 14, and we've got a remainder of 2 up here. So it's 7 times 14 and 2/7 equals 100. Okay. Now, if we times 1 by 14 and 2/7, we get 14. And 2/7 over 100, which we, of course, can't technically write. We can't write that as a fraction. But what we can see is that 2/7 is less than half of the 7, right? Which means that if we were writing this as a decimal, we would be getting a decimal that is less than 5. So in other words, it's going to be 0.14, and the final digit is going to be less than 5. Okay, which means that to 2 decimal places, 1/7 is 0.14. All right, and this is a nice way of converting fractions into decimals, and it's also quite an intuitive way, because we're seeing how we go from the fraction to the fraction out of 100, and then we can divide by 100 to get to 14. So to 0.14. Okay, so that's an example of how you can use perspective line and multiplication in fractions. Any questions? Is it all clear? So does it make sense?
Yeah.
Yeah. All right. Now, what do we do for, maybe I should have come to this on the multiplication page. Yeah, multiplication part 2. How do we do, say, 17 times 8? Any suggestions?
Usually I do like 10 times 8 plus 7 times 8.
Yeah, perfect. That's the right way to do it. So 80 and 56. And then, you know, we're going to see 80 to 100, 20, and then 36 remaining, giving us 136. Okay, what if we make it a tiny bit more complicated and do, say, 14 times 17? How would we do that one?
I'd 14 times 10 plus 14 times 7.
14 times 10 plus 14 times 7. Yeah. Very good. 140, and then you're going to do 70 and 40, yeah? Sorry, 70 and 28. Yeah. And then we're going to add those up mentally. And as before, we've also got, you know, our old school strategy that we can fall back on if we want to, okay, as a checking mechanism. But this is not a good mental arithmetic strategy for sure. Okay, if we get into much bigger numbers than that, the mental strategies start to become quite difficult. Okay, so at this point, well, two things are possible. Generally, this kind of question doesn't get asked, certainly up to 11 plus. I'm not even sure in 13 plus. And then, of course, calculators start coming in. So, yeah, I came to the conclusion that it wasn't really useful to try and do this level of complexity mentally, because the amount that you have to hold in your working memory is sort of prohibitive and starts to cause mistakes of itself. So yeah, but by this point, I say either do old school, because mental arithmetic strategy is a little bit too difficult, or it's obsolete. It doesn't really matter. Okay, cool. So we've had that's been a decent session, and I think it's probably a good idea to wrap it up there. I think we've covered the basics anyway. You know, everything that you would need to for teaching 6, 7, 8, 9-year-olds, we've covered, which was the main purpose. The more complex stuff, 11 and 11 plus and so on, that wasn't the aim of today. The aim of today really was to give you enough to understand how to use the Antonio books. And I think we've covered that. We probably covered that in the first 10 minutes. All right. So any questions? Nope. All right. So what I'm going to do, I've been preparing a few sheets which are taken from the Tiger range. You can see them on here. It says speed tests. All right. Now what you've got in here is a few exercises. Let me just open one of these up for you. I think I might just pause the recording at this point as well.